Chapter 9 is on solutions, and one thing to be aware of if you are following along with the PowerPoints is that there are worked problems where they also title the slide as solutions to the problem rather than solutions here, what we're referring to, which are when one thing is dissolved in another thing. A while ago, when we went through matter, we mentioned homogeneous mixtures, and that simply, as a reminder, means evenly mixed, that the two are indistinguishable from one another, essentially, at that point. The example over here is salt water, that if we dissolve salt, now it looks like there might be a little too much salt in here to actually successfully dissolve all of it, but if we dissolve salt in water, and then we end up with salt water, and that is a saltwater solution. And we can get it when there is attraction between the solute, that is the thing being dissolved, in this case the salt, the NaCl, and the solvent, the thing, usually a liquid, doing the dissolving. And together, the two of them, the solute and the solvent, make a solution. The solvent is the one that is present in the larger amount. This is really only relevant if we're dealing with a liquid-liquid solution or a gas-gas solutions, which they do exist but are super rare, and we're not going to get into any of them here. But a liquid-liquid solution, the two can be imagined to just be mixing with one another, and yet in terms of defining them, the one that there's more of we're going to call the solvent, the one that there's less of we're going to call the solute. And so then that gives us the quantity of solvent is greater than the quantity of solute in a solution. Solutes can be any of the basic states of matter, solids, liquids, or gases, and they will spread out evenly. Again, that is the homogeneous. And they mix such that the solute ends up with the solvent's state of matter. And we cannot then separate them by filtration. A heterogeneous mixture can be separated by filtration, but if you pass salt water through a coffee filter, you still get salt water. And coffee is actually a great example of a solution. You have your solvent, the coffee. Yes, it's only part of the coffee grounds, but the coffee grounds, and then you're passing water through it. That's your solvent, and you end up with the solution, the coffee. Well, that coffee forms inside of the filter and then goes through your filter, and so that filter has to allow the solution through, and that's true for any solution. However, we can separate them by evaporation. That is just heating them up. And usually what happens is you're driving off the solvent. It is possible to do the solute in liquid-liquid mixtures, liquid-gas, gas-gas mixtures, but most of the time we're going to be dealing with solids down in there, and so the solid will be left behind as the solvent evaporates away. And the particles that make it up are not visible. However, the solution can end up colored. So salt water looks like regular water. And I think I've mentioned before, but I was not a fan of chemistry as a student, and one of the reasons why I was not is because it felt like it was a whole bunch of white powders and clear liquids, clear solutions making other white powders and clear liquids. And so you just had to have this absolute trust that there was change going on without being able to see it. And some of the most interesting things were the things that involved a color change or other noticeable changes. This one here is copper sulfate solution, and copper sulfate exists as copper ions and sulfate ions down here settled out, and you can see they're starting to dissolve in the water, but it's not until we do enough mixing or allow just enough time for diffusion to happen and the random motion of the particles in there to cause it to dissolve, but eventually you end up with copper sulfate solution. And I will point out that when you have that solution, the particles that made up the copper sulfate that previously were stuck together, were bonded together, are now free floating in solution. You actually have copper 2 plus ions and sulfate, which is SO4 2 minus. So the sphere is obviously a simplified representation of that polyatomic ion, but they're floating around individually in solution there. Now, what's really interesting is you have times where you have a colored particle that gives you a clear solution, or a colored particle that gives you a solution that is a different color. And so those are some of the more interesting color changes that you'll see in chemistry. But most of our solutions are going to be clear. Here are some examples of solutions and the solute solvent. I'd encourage you to take a moment and look at that, but I'm going to move on because you can read. Water is one of our most common solvents in nature, and that's because it is polar and it has those polar bonds. Recall from previously that the oxygen side of water is slightly negative, the hydrogen sides of water are slightly positive, and so then we end up with hydrogen bonding occurring between the water molecules. But what can happen is you can have a particle like that copper sulfate, and I'm going to use this for the copper here. Remember, it has a positive charge, so what ends up happening is the copper gets attracted to the negative side of the water. And I'm going to use this color for the sulfate ion. The sulfate ion, being negatively charged, then is going to be attracted to the positive side of the water. Now, one water molecule won't have both a positive and a negative attached to it, but I figured I'd show you another one there. And frequently what happens then is some of the hydrogen bonds are lost then, because we now have something called ion dipole bonding at that point. But the fact that ionic things break apart in solution is called dissociation, and is what forms electrolytes. So when you hear about electrolytes in sports drinks, it's because there's different salts dissolved in there, and then those dissolved salts allow electricity to be conducted through the solution because of the charged pieces that are now in there, whereas water itself is not a good conductor. In fact, water is a very poor conductor. Having said that, never put electronics in water, or more specifically, electronics that aren't designed to be in water. You know, for example, a water pump might be designed to be in the water, but things like a hairdryer, I mean, never use that in a shower or bathtub because it turns out that you have plenty of salt on your body. The water that you get has stuff dissolved in it. If you're on well water, there's stuff dissolved in it. You can taste it. Even with things like city water, frequently there are things dissolved in there. Not frequently, there almost always are things, fluoridation, chlorine to purify the water, and so there's already stuff dissolved in it. And once you dissolve stuff in it, now it becomes conductive. And this stuff comes up in a later section, so we're just going to go ahead and move on. What happens when you have a solution is you have things that are able to mix because the attraction between the solute and solvent is stronger than the solute-solute interactions and the solvent-solvent interactions. And so essentially the solute-solvent wins the tug of war in terms of which things are going to be more attracted. Here you can see a whole bunch of solutions that are separated. Now it's possible that they just haven't been well mixed yet, and that if they were mixed they would interact. But you've of course heard before that oil and water don't mix, and that's exactly the kind of thing that's going on here. Is we have solutions that aren't mixing because they're not able to overcome their normal attractions. The way we normally describe this is that like dissolves like. That is, polar stuff will dissolve other polar stuff, and nonpolar stuff will dissolve other nonpolar stuff. But if you try to mix polar and nonpolar, they won't mix. Here, as I've mentioned already, these things dissociate. They break apart into individual ions when they dissolve. And so, like I said earlier, the negative side of the water will be attracted to the positive sodium ions here, and then they will break out in solution like this, being surrounded by, it's actually called a hydration shell, or here simply that we have a hydrated ions. with the negative sides of water all touching the sodium there, and the sodium being separated from the chloride ions. The chloride ions, being negatively charged, are attracted to the hydrogens, and so then the water molecules here, you'll notice, are oriented oppositely. And I'm sure I've mentioned it before, but water always looks like Mickey Mouse. And so a positively charged ion will have the head, which is the negative oxygen side, touching the ion, where the negative ion will have the positively charged ears touching the ion. And this one here is simply stating that polar things will dissolve. So hydrocarbons, generally speaking, are fairly nonpolar. That's what oil is. But the carbon-oxygen bond that occurs there in this one is polar. And it turns out the hydrogen-oxygen bond, as we've seen already with water, is polar, and so you end up with a slight positive charge there and there. And then it turns out that the water will be attracted to the methanol. So this one here asks us to identify the solute, so I'm just going to underline it here. 2 grams of sugar is going to be our solute, whereas water is a solvent. Here, the methyl alcohol, because it's in the smaller quantity, is our solute. Here, sodium chloride table salt is our solute. And here, the oxygen is the solute. Solid lithium chloride is added to water and dissolves because the lithium ions there, the positively charged ions, are attracted to the negative charge. Remember, opposites attract. And then the negative chloride ions would be attracted to the hydrogen atoms in the water. Without solubility rules here, it is still possible to do just basic predictions of whether something will dissolve or not. This here is ionic, and things that are ionic will dissolve. Things that are nonpolar won't dissolve in water because water is polar, and so will not dissolve. Iodine here, it doesn't tell you outright, but because it's made up of just the one piece, then it turns out that that one's nonpolar, which you may recall from when we covered bonding, and so it will not dissolve. And then here again we have something that will dissolve because it is ionic. And that finishes section 1.